All right, let's get right into it. Today, we're diving deep into one of the biggest, most persistent headaches in flow assurance, natural gas hydrates. Now, if you're in subsea or process engineering, you know these things aren't just some lab curiosity. No, they're a constant operational threat that shapes everything from pipeline design and chemical programs to some pretty high-stakes safety protocols. So, this is our engineering deep dive into what makes this subsea menace tick.
So, to really frame the problem, let's start with a bit of a physics riddle. What are we dealing with when we have a substance that looks and acts like ice, but it forms in deep water conditions that are actually above the freezing point of water? And get this, under the wrong conditions, a solid plug of this stuff can turn into a high-speed projectile with enough momentum to be catastrophic. It sounds kind of impossible, right? Well, that's the complex and dangerous reality of Clathrate hydrates.
Okay, here's our game plan for breaking this all down. We're going to start with the problem itself, then get into the core thermodynamics of how hydrates even form. From there, we'll cover the strategies to prevent them, the tech we use to find them, and the critical safety rules for getting rid of them. And finally, we'll wrap up by taking a look at where hydrate management is headed.
So let's kick things off with the core issue. As the industry pushes into deeper and colder waters, we're basically creating a perfect storm. The ambient conditions down there, really high pressure and low temperatures, land squarely inside the hydrate stability zone. This means hydrate management isn't just a nice-to-have, it's a fundamental non-negotiable part of keeping hydrocarbons flowing safely and continuously. And it has a massive impact on the economics of a project.
You know, it's pretty wild to think that for decades, this whole phenomenon was a complete mystery. Engineers were just baffled, finding these solid plugs in gas lines where, thermodynamically, ice had no business forming. They were pulling their hair out. It wasn't until 1934 that E.G. Hammerschmidt finally connected the dots in a landmark paper, identifying gas hydrates as the real culprit. You could say that was the moment modern flow assurance was born.
So what is this stuff on a molecular level? Well, think of a Clathrate hydrate as a tiny molecular prison. You have water molecules, the host, that link up with hydrogen bonds to form a crystal cage. And inside that cage, they physically trap smaller gas molecules like methane, the guest. The really crucial thing for us as engineers to remember is there's no strong chemical bond here. The whole structure is held together by relatively weak van der Waals forces. And that's exactly why their formation is so incredibly sensitive to small changes in pressure and temperature.
Okay, let's get into the nitty-gritty, the core science. At the end of the day, hydrate formation is just a phase change, and it's all governed by thermodynamics. You basically need a three-ingredient recipe for disaster. First, you need water. Second, you need gas molecules. And third, you need the right combination of high pressure and low temperature. If you have all three, you're in business. So let's look at the actual structures and their stability envelopes.
Now here's a key point. Not all hydrates are created equal. They form different crystal lattices depending on the size of that gas molecule. And while structure I is pretty common, the one you really have to watch out for, especially in processed gas streams, is structure 2. Why? Because its larger cages are the perfect size to trap heavier stuff like propane and isobutane, and those molecules act as powerful promoters, meaning they make it way easier for hydrates to form at even higher temperatures and lower pressures.
All right, this chart right here, this is basically the Bible, the operational map for any flow assurance engineer. See that curve? Any operating condition to the left of it is the danger zone. That's where hydrates are stable and can form. But the most important thing to get is that this curve isn't static. The bad guys, like acid gases, shift the curve to the right, making the danger zone bigger. The good guys, our chemical inhibitors, shift it way to the left, giving us a much safer window to operate.
A full-on pipeline blockage doesn't just appear out of nowhere. It's more like a slow-motion train wreck. It all starts when hot fluids cool down and water condenses out, pooling in low spots. Once the system gets cold enough to enter that danger zone, the first crystals nucleate. Then they grow and stick together, forming this thick slurry, and it's a nasty non-Newtonian fluid. Its viscosity can shoot up by orders of magnitude until the pipeline's pressure just can't push it anymore, and boom, you've got a plug.
Okay, enough about the problem. Let's talk about how we fight back. Because let's be real, the absolute best way to deal with a hydrate plug is to never let it form in the first place. This section is all about the proactive chemical strategies we use to stay out of trouble.
When it comes to chemical warfare against hydrates, you've really got two main schools of thought. The first is the traditional brute force method using thermodynamic inhibitors, or THIs. This is like throwing salt on a frozen road. You're injecting a ton of chemical to fundamentally change the water chemistry and make it impossible for hydrates to form. The other approach is more of a surgical strike. It uses low-dosage hydrate inhibitors, or LDHIs. which don't change the thermodynamics at all. Instead, they operate on a risk management basis by messing with the crystal formation process itself.
So if we dig into that brute force family, you've got the two heavy hitters, methanol and MEG. Think of methanol as cheap and effective, but it's also volatile and toxic, and a lot of it gets lost to the gas phase, making it really hard to recover. MEG, on the other hand, is the clean, recyclable option. It mostly stays in the water, which is perfect for these big, long subsea tiebacks where you can capture it, regenerate it, and pump it right back in. That's a huge win, both economically and environmentally.
Now, inside that more surgical LDI family, you have two different kinds of specialists. First, you have Kinetic Hydrate Inhibitors, or KHIs. These are like tiny bodyguards. They're polymers that absorb onto baby hydrate crystals and physically stop them from growing bigger. They basically buy you time. Then you have Anti-Agglomerants, or AAs. These are more like a Teflon coating. They actually let the hydrate crystals form, but they make them so slippery that they can't stick together to build a plug. Instead, you get a transportable slushy. So what happens when all your prevention strategies fail? Now you have a multi-million-dollar problem, and it's hiding somewhere in kilometers of pipeline at the bottom of the ocean. How on earth do you find that needle in a haystack? That's where non-intrusive diagnostics come into play.
Thankfully, we're not just guessing anymore. We've got a whole high-tech toolkit. We can run fiber optic cables along pipelines for things like distributed temperature sensing. This is basically a super-sensitive thermometer that can spot the telltale cold spot that a hydrate plug gives off because its dissociation is endothermic. Other methods are more active, like pressure wave analysis, which is basically pipeline sonar. You send a pulse down the line and analyze the echoes to map out exactly where the blockage is.
But one of the real game changers is a tech called Acoustic Resonance Technology, or ART. Imagine sending a robot down that clamps onto the outside of the pipe and can tell you exactly what's inside, right through the steel and all the insulation coatings. That's what these systems do. They use acoustic signals to definitively tell the difference between gas, liquid, and solid hydrate, all without ever breaking containment. And this isn't just theory. This stuff works in the real world. Check out this case study from a deepwater field off Angola. In just 33 hours, this system scanned 9 kilometers of flowline and pinpointed the exact location and size of 2 separate plugs. That is an absolutely incredible capability. It takes you from what could be weeks of blind guesswork to a precise, data-driven surgical strike.
Okay, so you've found the plug. Now comes the hard part, and the most dangerous part. Getting rid of a hydrate blockage is one of the highest risk jobs out there. If you misunderstand the physics of what's happening, things can go from bad to catastrophic really, really fast.
To really appreciate the hazard, you have to understand the energy density here. Look at this number, 1 single cubic meter of solid methane hydrate, so a block about the size of a washing machine, is holding roughly 168 cubic meters of gas. That is an incredible amount of stored energy. Uncontrolled, it's not a leak. It's what we call a frozen explosion.
And this is how that explosion happens. It's the dreaded hydrate projectile phenomenon. If you depressurize or heat a plug from only one side, it tends to melt from the warm pipe wall inward. This creates a slippery, lubricating layer of fluid. Now, if you have a big pressure difference across that plug, you've just turned your pipeline into a cannon, and the solid hydrate plug is the cannonball. It can accelerate to supersonic speeds, and it will destroy the first elbow or valve it hits.
So, how do you disarm the cannon? It's 100% about eliminating that driving force. The industry gold standard, the #1 rule, is two-sided depressurization. You carefully, slowly bleed pressure from both sides of the plug at the same time. By keeping that differential pressure near zero, there's no force to launch the plug. It just sits there and dissociates safely. Any other approach, especially heating from one side, is just asking for trouble.
All right, to wrap things up, let's look ahead, because the entire philosophy of flow assurance is starting to shift. For decades, the mantra has been hydrate avoidance at all costs. But we're moving towards something much more sophisticated, a paradigm of active and intelligent hydrate management.
And there are some seriously cool ideas on the horizon. Cold flow is a mind-blowing concept that uses anti-agglomerants to intentionally let hydrates form, but as a transportable slurry. This could completely change pipeline design, maybe even getting rid of insulation. We're also seeing a big push for green, biodegradable inhibitors to reduce our environmental footprint. And of course, machine learning is being integrated with our simulators to create predictive systems that can fine-tune inhibitor rates in real time.
And that brings us to a final, really interesting question. For more than a century, we've treated hydrates as the enemy, something to be fought and avoided. But as our technology gets better and our understanding gets deeper, what if that's the wrong way to look at it? As we shift from simple avoidance to active management, are we on the verge of an era where we can learn to control and maybe even harness these amazing crystal structures? Now that's the challenge for the next generation of engineers.
Thanks for watching.